So a couple of ways that this has been taught, and there's often little slightly different methods, but I'll go with the classic one. You might have learned to write the 2,748 in almost a square root looking thing. It's not, apparently it's not quite the same. There's not this extra little thing there. That doesn't really matter. And then you put the 13 out in front. How many people remember at least that setup somewhere? Okay, you've seen, some of you have seen that before. And depending on where you learned your division, maybe you saw something slightly different or somewhat similar. But the idea was this, and this time when I'm going to teach you the idea, I'm going to kind of connect it, hopefully to some number sense, that it makes a little bit more sense to you, because probably when you learned it, one of the things you would have done, if this was grade 5, 6, or 7, is you'd have been like, I need to remember how to do this, but I don't know why it's happening. Now that's a danger in math, because if you're remembering how to do something but you don't know why, usually it means you won't remember it later. So for some of you who aren't remembering how to do it right now, it's partially because of that reason. And I'm going to say that same thing for this course. This course is a lot of tough stuff. Some of it you will not be able to understand the first time you look at it. But in the back of your head, you should be like, I want to, or I need to, or I should understand why this works. But in the short term, when we have a test on Friday, the best I can do for that test on Friday is to see, like, can I know how to do it so that by the time I get to the test, I'm at least not failing this. But I still don't understand it. Later on, though, you should be like, I need to go back to that trigonometry. I need to go back to that idea because I didn't really understand it. That means you still have work to do. Spending the time to think about something until you get to the point where you understand it will help you remember it later. By the way, later for this year means we have an exam at the end of the year. If you just knew how to do it right now, you will not know how to do it when the exam comes and you're going to have to redo all of that study. And some of it will still be that point where you just like, I just know how to do it for this moment, but I still don't understand it, and that's okay. But the more things that we can understand, the easier math becomes. So, first of all, I'm going to go back and just teach you the rule. Your teacher would have said, well, just look at the beginning numbers. Is there any 13s in 2? And you would be no. Then they'd say, well, is there any 13s in 27? And you would say, yes, there would be 2 of them. And your teacher would say, yes, there's 2 13s in 27. So we should put the 2 here. And you're like, why would I put the 2 there? Oh, that's very important you put the 2 above the 7. And you're like, okay. And then they're like, then take 2 and multiply it by 13 and you would get 26. And then you subtracted 27 minus 26 is 1, and just bring down the 4 and the 8. And at first, if these are the steps you were memorizing, this seems weird. Like, what are we actually doing? What we're actually doing here is this 2, and that 27, when we look at it, that 27 actually means 2,700 if we ignore the 4 and the 8. The 27 is 2,700, right? This is in your thousands place, that's in your hundreds place. And when you're asking how many 13s are in 27, and you say 2, you are actually asking how many 13s are in 2,700, and the answer is 200. But for kids in grade 7, it's hard to think in the hundreds, so the teacher would be like, it's easier just to think of 27 and say the 2. And why did we write the 2 above the 7? Because that actually means 200. And so when I write that 2 above the 7, I've written it in the 100 spot, and 200 times 13 is technically 2,600. And now when I subtract, does it make sense that I have 148 left? Yes. Because 200 only gets me to 2,600. Doesn't get me all the way there. I have 148 left. And we redo this process. So now since I'm redoing the process, I'm going to switch colors. I'm going to look at the numbers here until I underline a number that there's 13s in. There's a 13 and 14. How many? One of them. This time I'm writing it above the tens column. Because 10 13s, well, 1 13 is 13, but if we think of it as a 10, it's really 130. That accounted for another 130 numbers. Which means, when I subtract, that's not what I wanted to do. When I subtract, I have 18 left. I draw the line, I subtract, and I have 18 left. And now, how many 13s are there in 18? I'll switch colors again. That is an 8. There's 1. 13, I subtract, I get 5. And there's a remainder of 5. This is called long division. This is the technique that you did here means that you are checking numbers as you go. Okay? There's other, like sometimes I've seen things like this, right? Think in your thousands. Like they say, instead of having to get the exact number 2 right away, you could be like, how many 13s would there be there? Someone say, I'm going to start with 100 of them. 100 of them would be 1,300. How much do I have left now? I'm left with 1,448. Oh, I could do another 100. That would take another 1,300 out. Now I'm left with 148. Then I could do 10 of them. That would give me 130. Now I'm left with 18. Well, I could do another 1. That would take it out of the 13 out. Now I'm left with 5. And if I added all these up, I get 211. So there'd be some teachers sometimes that taught a different technique like this, because this is like you're getting it by slowly getting closer. Okay? And this one, you didn't have to get the 2 right away. You didn't have to get the right number right away. However, there's still something really nice about the actual technique here that we're going to use, because now what we're going to do is we're going to divide with algebra. We're going to divide with polynomials, and we're going to use a very similar technique. And the second one, I'll just do it quickly here. And I'll color code the same way that I did before. First number is a 42. There's only 127 in the 42, which is actually, if I put that 1 in the 100 spot, 100 times 27 is actually 2,700. And when I subtract, I get 1,512. Switch colors. Now I have to go to 3 numbers before I can pull out a 27. How many 27s in 151? The mental math gets a little bit tricky here. 5 of them is 135. 6 would be
162.
106, too much, right?
Sheets 5.
So I'm going to do 5 of them. I'm going to put that 5 above my ones column. 5 times this is 135. That 5 is really a 50. And when I subtract, I've got 162. Well, it sure is nice that you just said that the time before, because now that's a 6, right? And that works out perfectly, giving no remainder. Now, what does it mean when there's a remainder and when there's no remainder? Well, when there's no remainder, things are really nice. We can actually write this out. What did we just discover here? We just discovered that 4,212 is equal to 27 times 156 perfectly. That's what that means when there's no remainder. What does it mean when there is a remainder? In this first one, that means that 2,748 is equal to 13 multiplied by 211. But it's not quite right. because 13 times 211 doesn't work out perfectly. There's a remainder of 5. If you actually multiply this out, you get 2,743. You would have to add 5 to make it work. Now that's an equal statement. It doesn't work out perfectly, but the remainder says if you added 5 there, you would still get it to work. Okay? So I'm going to just play around with a little bit of math with you guys right now. I'm going to take something pretty easy. There we go. 22 over 3. Okay? I hope you can easily see that this is going to be 7 is close and that you'd have a remainder of 1. Okay? I chose an easy number so we didn't have to write out much. Mathematically, this means that 22 is equal to 3 times 7, and then you'd have to add 1 to it. What was the original question? Was 22 divided by 3? If I divide everything by 3 here, I could get the 22 divided by 3. Its answer should be 7. The remainder of 1 still needs to be divided by 3. You see how I went from the one division statement to the other division statement? I divided everything by 3. That 1 would have to be divided by 3 as well. What's really nice about this is you might be able to say, I now can change this to a decimal. It's 7.3 repeated. I know that 22 divided by 3 is 7.3 repeated. Which is kind of cool. Okay? Now, understanding both of these is going to be really important for us when we go to algebra. So now we're going to learn to do the same thing that we were doing with numbers, but now you're asked to divide 3x squared minus 4x plus 5 divided by x minus 2. And we set it up exactly the same way that we did with numbers. I'm going to write 3x squared minus 4x plus 5, and I'm going to divide it by x minus 2. And a lot of the process is the same. I'm going to color code this. I'm going to go from left to right. I'm going to underline the 3x squared. Because what we did with numbers, right? I'm going to just flip back to the beginning here. I underlined the 27 in blue, because that I could get 13s into, right? What we're going to do with algebra, we're going to underline that 3x squared in blue and say, is there possibly something I could multiply x minus 2 by to get a 3x squared? There is. What could I multiply an x minus 2 by so that one of my terms is a 3x squared? Well, I'm not going to look at the minus 2. I'm just going to think about the x. 3x. What could I multiply x by to get a 3x squared? I could multiply by a 3x. Where do you think I'm going to put the 3x? Above the x column. And what is 3x times x? That's 3x squared. And what is 3x times minus 2? That's minus 6x. What we're trying to do is we're trying to get close to 3x squared minus 4x plus 5. So we started with the 3x squared. Could I get close to 3x squared? Yes, if I had a 3x. Well, what did we do in long division? We subtracted. What are we going to do in long division here? We're going to subtract. But I'm going to make sure I put this in brackets because we're subtracting all of this. What happens when you do the 3x squared minus 3x squared? That's always going to be 0. What happens when you do a minus 4x minus a negative 6x? You get a plus 2x. And then 5 minus nothing would still be a 5 there. Some people say bring down that 5. Some people would say, well, you're actually doing 5 minus nothing. You're still going to get a 5 there. Switch colors. Now, I have a 2x. Is there something possibly I can multiply that x by to get a 2x?
Plus 2x.
At plus 2. You see that? So then above my 1s, I write plus 2. What's 2 times x? It's 2x. What's 2 times a negative 2? Negative 4. Put it in brackets and subtract. The number one mistake that happens in long division is an arithmetic error with subtracting. You get so excited that you're close to done, people will write 1 under here, but what number actually has to go under here? 5 minus a negative 4 is going to be a 9. That is your remainder. Which means, right? What did we just find out? We found out that if you had 3x squared minus 4x plus 5, and you had x minus 2 times 3x plus 2, that is the closest you could get to being right with an x minus 2. If I FOIL this out, do you see that you would get your 3x squared? Do you see that your outside 2x, inside minus 6x would give you minus 4x? But my last one's negative 2 times 2 give me negative 4. I wanted to get a plus 5. So my remainder plus 9 has to come on the outside there to make that equation true. So why are we doing this? Well, you'll see when we do this second example. So I'm going to set up the second one the same. I've got 2x cubed minus x squared minus 2x plus 1, and I'm going to divide by x plus 1. Color coded again. The first thing is a 2x cubed. What could you possibly multiply x by to get a 2x cubed?
2x squared.
2x squared. So one of the things I hope that you're noticing is that so far the math feels like, yeah, this is not bad. No crazy rules to remember, no big formulas, pretty easy algebra. A lot of people like this unit for that reason. It's going to be a 2x squared. What happens when I multiply 2x squared times x plus 1? Well, 2x squared times x will give me 2x cubed, which is exactly what we want. We want that first one to match up. And 2x squared times the plus 1 will be plus 2x squared. Put it in brackets and subtract. Well, this will be 0. Negative x squared minus a 2x squared will give me negative 3x squared. And I still have a minus 2x and a plus 1. Next up. Now, my first term is a minus 3x squared. What could you possibly multiply the x by to get a minus 3x squared?
Minus 3x.
A negative 3 and an x. I'll write that above my x column. And negative 3 times x for sure, that's negative 3x squared. And negative 3x times a plus 1 will be minus 3x. I put it in brackets and I subtract. Of course, that goes away. Negative 2 minus a negative 3 will be plus x. And 1 minus nothing would be plus 1. Switch colors again. Now my first thing is an x. What could I multiply an x by to get an x of 1? So I write plus 1 here. And 1 times x is x, and 1 times 1 is plus 1. I put it in brackets and I subtract, and I get a remainder of 0. And if I write what this means that 2x cubed minus x squared minus 2x plus 1 is equal to this, x plus 1, times by this, 2x squared minus 3x plus 1. And what most of you did for the first time in your lives, since that worked out perfectly, you have just started to factor an x cubed. Up till now, what it was the most we ever factored was x squareds. You knew how to do like binomial times binomial, and you could get x squareds. And you could factor differences of squares. But this is the first time you've ever factored an x cubed. In fact, once you took out the x plus 1, equals this, equals, look at this one. This is a quadratic, and you get 2x and minus 1 and minus 1, and now we have factored it completely. One of the ideas in this unit is how do you factor things bigger than x squared? And now that we've learned how to do long division with algebra, if it works out that the remainder is 0, you've started factoring. If it works out the remainder is not 0, you have failed in your factoring attempts at this point. Okay? But being able to factor this means you can solve this equation. When is 2x cubed minus x squared minus 2x plus 1 equal to 0? I now know that it's equal to 0 at minus 1 when x is 1 and when x is 1/2. So not only can we solve questions we weren't able to solve before, we can also graph questions we weren't able to graph before. And that, in a nutshell, is this entire unit. The start is learning this technique of division. So if we go, they have it on the next page here. They've got an example here where they walk through what we just did. And you get a remainder. And if you want, and this is going to be very helpful for us, in this one, if you want, you could write beside here that we now know that if you tried to make this x minus 1 times something, the closest you could get is x minus 1 times x plus 3. That would get you very close. It would get you the x squared. It would get you the 2x, but it wouldn't get you the 5. That's as close as you could get with an x minus 1. And then in order to make it work, we'd have to add 8 more, because that's the remainder. Do you see those last terms there when you multiply it out? Do you see minus 1 times 3 would give you minus 3? Adding 8 more to that minus 3 would get you to the 5. So long division here lets us get as close as possible without getting there perfect. And if we go to example 1, the first thing that I'm going to write, we're going to do another long division one. There are some important things for long division in order for it to work that never come up with regular numbers. So there's 2 important things you need to consider when using algebra and log division that never came up with numbers. Number 1 thing that has to come up in long division is the order is very important. You need to go from largest degree to smallest degree. And this first question that we've written is not in the right order. You see, it goes from an x cubed to the 5 to the 2x to the x squared. This never comes up in numbers because you automatically have an order with numbers. It would be terribly confusing in math is if someone said, write 702, and as long as you wrote a 2, a 0, and a 7, you'd be like, oh, I wrote my hundreds here. This is 702. This is the way that I write it. And you would be like, that's messed up. When we write numbers, we automatically have an order. But because algebra, adding and subtracting doesn't matter the order, you know what this means. But we're going to have to rewrite it in order. Okay? And the second thing that doesn't happen in this question, but it's going to happen in the next question, we're going to add zeros when things are missing. And I can even sneak peek to the next one here. Which one's missing? It has an x to the 4. It has an x cubed. It has an x. It has a 20.
Please go to the cafeteria. cafeteria. Mr. Edwards, please go to the cafeteria.
Do you see that the x squared is missing? When we do long division, we're going to have to add a 0 for that to hold its place. So we'll see that when we get to this one. These are the two things for setup. The order matters. So when I go to set up my long division here, it's a box. I'm going to start with my 2x cubed because that's my biggest degree. Then I'm going to write my 3x squared next, then my minus 2x, and finally my plus 5 when I divide by x minus 1. I want to make sure that my order is written properly. Then the steps are the same. What's the first thing? A 2x cubed. What could you multiply an x by to get a 2x cubed? A 2x squared. I'll write that above my x squared column, which, because things are in order, that matches up nicely. And 2x squared times x for sure is 2x cubed. And 2x squared times the minus 1 will be minus 2x squared. Put that in brackets and subtract. This will always be 0. 3 minus a negative 2 will give me 5x squared. And I still have the minus 2x and the plus 5. Switch colors. Now my first term is a 5x squared. What could I possibly multiply the x by to get a 5x squared?
5x.
A 5x. So 5x times x for sure, that's 5x squared. And 5x times the negative 1 is negative 5x. I put it in brackets and I subtract. 5x squared minus 5x squared, of course, is 0. Negative 2 minus a negative 5 is plus 3x. And of course, I still have that 5. Switch colors. Now my first term is a 3x. What could I multiply x by to get 3x?
3.
Multiply by 3. So I write plus 3 here. 3 times x is, of course, 3x, and 3 times negative 1 is negative 3. Again, remember, I find that the main place that mental math happens is right at the end with the remainder. People get so excited that they're close to the end, they do 5 minus 3 and write remainder as 2. All right, but here it's still 5 minus a negative 3. The remainder is 8. So this means that this did not factor out perfectly. It means if you wanted 2x cubed plus 3x squared minus 2x plus 5, and you wanted it to be x minus 1 times something, the closest you could get is 2x squared plus 5x plus 3. And if you used your distribution skills here from grade 9, right, where you multiply the x by everything, multiply the minus 1 by everything, combine your like terms, you would get so close. You would get 2x cubed. You would get plus 3x squared. You would get minus 2x, but unfortunately you would get a minus 3 instead of the plus 5. And that's where our remainder comes into effect. We get a plus 8. Now, what I just wrote here, and I'm going to put it in a big box, is something called the division statement. Right? It's the result. What did we find? We found out that we got close. Everything worked out except for the last number. We'd have to add 8 as a remainder to make it work. And we can highlight this on page 4. So first I'll tell you the numbers. You can circle from this one 3A, C, and D. 3A, C, and D, and also number 5. I think, double check, yes. And also number 5. But now I want you to turn to page 4. And on page 4 they say, if you do your long division, you can write the division statement. And the division statement is always, and I'm going to, you have your original polynomial, p of x. So I'm just going to write a p above that, because this is how I'm going to get you to remember your division statement. Your polynomial is equal to, x minus a is called the divisor, because it's what you're dividing by. So we're going to use the letter D to remember divisor. The answer you get when you divide something, right? The word that we use in math when you get an answer from dividing is a quotient. So I'm going to use the letter Q here. So your polynomial is your divisor times your quotient, and then whatever you need to make it work is plus the remainder. And I find this easy to remember because I see DQ and I think of ice cream, and that makes me happy. Some year, when I teach this in summer, I have at times gone to Dairy Queen right after this lesson and posted a picture on Teams with my ice cream because it triggers me that much. That makes me think of going to Dairy Queen. And yet I put these videos online. You'd think Dairy Queen would send me a free coupon for an ice cream. No. All these years of free advertisements, nothing. I'm still waiting. Okay. So, this is our division statement. And moving forward, questions will say, can you also write the division statement? I've been doing it with you already all the way through. So we'll stop our first video here.